Fifth and final section of factoring in terms of new material. After this section, I'm going to have a little 7.5 and a half where we compare all these methods that we have now and try to figure out how to figure out which one to use when. And then 7.6 will actually not really have new material, but it will be what we're going to add is an equals 0 to these and make them equations and then solve those, which just has one more step. But it's the factoring that's the hard part. So once you get to here, you pretty well have this chapter squared away. So 7.5 is actually much easier than 7.4. It's some formulas, and the hard thing on this one is just remembering to use them. And if you do, it's like the easiest problem in the world. You just look at it and write down the answer. So let me start with these two-term ones, and we're going to see three-term ones, and those, notice, have perfect squares on the ends. That's going to help us identify these when we're trying to sort them out. And then we haven't had problems yet where there were two terms, and this is that. So for two terms, it's either going to be some sort of easy greatest common factor, so something like 3x squared minus 9x, where we can factor 3x out front. So that's one option, or it's this difference of squares that we're going to look at right here. So for two terms, let me go ahead and write this part out. A plus b, a minus b. If I FOIL that out, the reason it comes out to a squared minus b squared is a times a squared. On the outside, I get a minus ab, and on the inside, b times a, same as ab, I get a positive ab. And those cancel every time, no matter what a and b are. And when I do the last two terms, positive and negative makes a minus b squared. So these cancel, and then I'm left with what's called a difference of squares. So it's a subtraction problem, a squared minus b squared, and they're both squares. So every time I see something of this form, like right here, I know how it's going to factor. It's going to be this a plus b, a minus b every time. So when we're trying to figure out what these are, we want to think that 16x squared, that's like the a squared. So we ask what times what would make 16x squared, and that would be 4x, right? 4x times 4x would get me back to that 16x squared. And the same thing here, what times what would give me 81, 9. And so this is going to be minus 9, or plus 9, I guess, if I do the same order I wrote here, but it doesn't matter. So plus 9 and minus 9. And that's it. That's how you do these. If you just recognize that those are squares on the ends, you go, oh, 4 times 4, 9 times 9, so 4x plus 9, 4x minus 9. So they're actually really easy relative to what we were just doing, especially. And the hardest part, like I said, is just realizing that's what you're working with. So for this one, it does not have squares on the ends at the moment, but it does have a greatest common factor. So let's get that pulled out. It's going to be a 3y. That's going to leave me a y squared. 3 out of 75 would leave me 25. And the y came out. Again, I always like to kind of distribute back in my head, make sure everything is good. And now I got y squared minus 25. Those are both squares. It's a minus, so easy. 3y, and then y plus 5, and y minus 5. And if you FOIL it out, again, you'll see you'll get minus 5y on the outside, plus 5y on the inside. They cancel, and you're left with those squares. The other two formulas we're going to see. So for the two terms, we got 1 plus and 1 minus for our factors. For the three terms, we're either going to get double minus, so this is a minus b squared, so it's like a minus b, or a plus b, so either double negatives or double positives. And the way to tell them apart is if it's a minus on the middle term, it's a minus, a plus gets you a plus. If you write these side by side and FOIL them out, you'll find you get this every single time, so that's why the formulas work. So here, if I ran into this problem, it's got three terms. I do not have a greatest common factor. I could try to do it the way that we did in the last section where I got 9 times 64. That would give me a ginormous number, and that would be really hard. So if you just recognize a squared minus 2ab plus b squared in there, then that means, and you can tell that from the squares on the ends, and we'll double check that the middle is what it should be when we get it factored. But if you recognize those squares, then you can just go, what times what would make 9x squared? That would be 3x. That's a minus, so this is a minus. What times what makes 64? 8. And quantity squared. And again, this quantity squared means that this is really 3x minus 8, 3x minus 8. It's double negatives instead of mixed signs like up here. Just to make sure that I could have one with squares on the ends and that the middle term didn't work, and so it's always good to just double check that it was what you thought it was. So the formula says it should be 2 times a times b. Well, this is a, right, because this is a minus b squared. So if you just multiply those two together, that's the AB, and then double it. So 3x times 8 would be 24x, double it, and there's the 48. So it is what I'm assuming it is. When I see squares on the ends, I just usually think, okay, I bet it's one of these, and then I check myself, and then if it's not, then I can go back and use AC method. So this one, 25 and 36, those are both perfect squares. And perhaps I should say, in terms of squares, what I mean by that is things like 1 squared is 1, 2 squared is 4, 3 squared is 9. So these are the perfect squares I'm referring to. 4 squared is 16, and so forth. So that's 5 times 5. This one is 6 times 6. So this is just going to be 5z. It's a minus, so it's a minus, and then 6 quantity squared. And they're just that easy if you recognize them. We'll double check the middle. 5 times 6 would be negative 30, and then double it, and there's our 60. This next one looks terrible, except it has the greatest common factor, so we'll get that out of the way. So that's going to be 3x, because this only is to the first. And so that will leave us an x squared. Let's see, 3 goes into that one 16 times. So 16x. And 3 goes into 192 is 64. And this does have squares on the ends. This is just, a plain x squared. So if I thought of this as a 7.3 problem, I could say what two numbers multiply to 64 and add to 16. And for that I would say, okay, 8 and 8 add to 16 and multiply to 64. Or I could treat it like squares on the ends and write it as plus, x squared would be x, 64 would make 8, quantity squared. And again, those mean the exact same thing.